Swayam Prabha. Digital India. Educated India.
In the past few lectures, we have been setting up the dynamics for rigid bodies, and I have also shown you some demonstrations. In this lecture, I want to show you some more demonstrations and explain them through whatever we have learned about rigid body dynamics, particularly rotation about a fixed axis. In the first example, what I am going to do is I will take a long scale which we will assume is rigid for our practical purposes and hold it on the edge of a table on one side, and I will put some small objects. In my case, I have taken them to be carom coins on this, and what I will do is I will keep holding it here by my hand, and we want to know what will happen after I release my hand. Obviously, what is going to happen is this rod is going to come down, rotate about this edge like this, and I want to know the position of these coins relative to this rod as the rod moves down. So, let us see the demonstration and then we will explain it. So, as I said, I have the scale which is a meter long scale on which I have put these carom coins, and I am going to release my hand from here, and you see what happens. So, what you just saw in the demonstration is that this rod that I had, or the scale that I had, on top of it there were these coins sitting here, and as I released the scale, or I removed my hand, these coins started coming down, and so did the rod. And what you would have noticed is that as the rod is coming down like this, is rotating, the coins are also falling down. What exactly is the position of these coins with respect to the rod, you will see more clearly in running the whole demonstration in slow motion, which I will run now. So, to understand what happened, let us now make this rod again. When it is released, it is rotating about this point here. Let us take the length of the rod to be L. Assume the rod to be uniform, so that its moment of inertia I is ml square by 3 about this point, which I will call O for clarity. Therefore, if the rod is uniform, it is experiencing a force mg as its center of mass, which is at a distance L by 2 from the edge, and therefore, the torque on this is going to be mg L over 2. Now, what we have learned about rigid body dynamics tells us that I times the angular acceleration alpha is going to be equal to tau, and therefore, alpha in this case is tau over I, which is mg L by 2, and we are dividing this by m L square by 3. M cancels, and you get alpha to be equal to this L also, 1 L is left, and you get G 3G over 2L to be alpha. So, this rod, when it starts coming down, is coming down with an angular acceleration alpha is equal to 3G over 2L, and therefore, at any point at a distance x at the beginning, when I can take this angle to be small, the linear acceleration of that point at distance x, which I am showing that point by this dot here, is going to be alpha times x, which is 3g over 2l times x. What you notice then is that, let me make the picture again. Here is the rod, here is the point at a distance x from the edge of the table, and its linear acceleration a is 3g over 2l x, and for x equals 2l by 3, a is g. That is point number 1. Point number 2, x greater than 2l by 3, a is greater than g, and for x less than 2l by 3, a is less than g. Therefore, in the beginning, if I take this distance to be 2l by 3, all these points to the right of it are moving down with an acceleration a, which is greater than g. All the points to the left of it here are moving down with an acceleration which is less than g. On the other hand, all the coins fall down with an acceleration g. So, what is going to happen? The coins which are beyond this point x equals l by 3 are going to move away from the rod. There is going to be a distance created between the rod and the coins. Those to the left have an acceleration which is larger than the linear acceleration of the scale, and therefore they are going to be sticking there. So, what you are going to see finally, and you must have noticed in the demonstration, is that as the rod comes down here, I am making it on the right side of the screen, the coins here are stuck on the rod, whereas those on the right have gotten detached from it, and this is precisely what you see. So, this is the explanation of the demonstration that you just saw on the basis of rigid body equation that we have learnt. For the second demonstration, I am going to talk about something called the Maxwell's wheel, and it also comes in the market as a toy called yo-yo. What it is that there is a large wheel which is taken, let us say it is uniform distribution of mass, and on its axle one wraps a string and let it go. So, what happens in this case, you will see that the wheel descends down very slowly, and that depends on the radius here. So, I will show you the demo first, both a yo-yo and Maxwell's wheel, and then we will do the related calculation. So, what I have here is a tricycle wheel on which children play, and I put an axle of very small radius on it, put a hole, made hole through this, and put threads here. What I am going to do is wrap the string on this axle and then let the wheel go, and we will see that how it moves. So, what I have done here is that wrap that string around the axle, and I will leave the wheel now and see what its motion is. You see it comes down very slowly and then comes up again, and that is because of the conservation of energy. A toy version of what I just showed you is what is called a yo-yo, in which these two large discs are there, and in between there is an axle which has a much smaller radius, and you will see that the way I play with it is I let it go, come back, let it go, come back, let it go, come back, but you can see it is not moving down as fast as a falling stone or something. Let us now explain this through rigid body dynamics. So, to solve this problem of the demonstration that I just showed you, let us take this wheel that I showed you to be the large wheel of radius r with mass m, and let the axle radius be small r, and there is tension T in the string holding it. The forces on the wheel are, there is a force mg pulling it down, and as it rolls down, this point I will show by blue in contact with the string is stationary. So, the equations that I have are 1 mg minus t is equal to ma, where a is the downward acceleration of the wheel. Notice that a is going to be smaller than g because there is a tension. Now, I can take torque about this blue dot that I made and write the other equation, that is going to be I alpha is going to be equal to, torque is only due to the weight, is going to be mg times small r. What is the moment of inertia I? Moment of inertia I, if you recall from previous lectures, is moment of inertia of the CM plus moment of inertia about CM. So, about the CM, moment of inertia is nothing but m r square by 2, assuming all this wheel is uniform, and of the CM is going to be m r square, and therefore, I am going to have I alpha is equal to mgr, where I is m r square plus r square by 2 is equal to mgr, and these two equations together, therefore, this m cancels, give me, oh, there is an alpha here, alpha is equal to g r divided by r square plus r square by 2, or is equal to g times 2r divided by 2r square plus r square. So, what we have found is that as this wheel descends down, is angular acceleration alpha, and keep in mind that earlier I had said angular velocity alpha calculated about any point is the same. We have calculated this to be g times 2r divided by 2r square plus r square. Third equation is going to be that this point is stationary, and therefore, the velocity of this point always remains the same, and that implies that a must be equal to alpha r, and therefore, the linear acceleration of the body of the center is going to be g times 2 r square over 2 r square plus r square. Now, once we know a, I can also calculate the tension in this string, which is going to be equal to mg minus ma, which is m g minus a, which is equal to m g 1 minus 2 r square over 2 r square plus r square, which comes out to be mg r square over 2 r square plus r square. So, what you notice is that the linear acceleration of the wheel coming down is g times 2 r square over r square plus r square, which is roughly equal to, assuming r is much less than r, roughly equal to g times 2 r square over r square, much smaller than g, and therefore, you see this wheel coming down very slowly. Now, when it comes down and then goes back again, that is because of the conservation of energy, that it goes up. In the process, it also loses some energy, and therefore, the height that it goes back to is not the same as earlier one from which it was released, but that is lost because of the losses. But this demonstration shows you something about the dynamics of rigid bodies, translation plus rotation, as well as energy conservation. As the third demonstration, I am going to show you something which you also may have played around with. If you try to balance a long rod on your finger, you notice that if the rod is small, then it is very difficult to balance it. On the other hand, if rod is very long, it is easily balanced. I will show you the demo first, and then we will try to understand it, or we will understand it through rigid body dynamics. What I have here are these three scales of different lengths, and I will try to balance them on my finger one by one, and you will notice that the longest scale I can actually hold for much longer than the smaller scales. So, let us do this small scale first, and I am trying my best, I am not cheating. So, you see this goes off very fast. Show me again, I will show it to you again, but it falls off. Let me show a little medium size scale, and I can do slightly better on this. You see this, I can do better. Let me show it again. I can do better on this, and let me now take the longest scale that I have, and I will do very good on this. You see, I can hold it for a much longer time, and now we will try to understand why this happens. So, to understand this, what I will do is I will make this rod which is held on this finger and see what happens to its motion if it gets slightly displaced from its vertical position. Let us say by an angle theta. Theta is much less than 1. That itself sets the motion. So, this is a good approximation to start with. Now, as this happens, the force on this rod is vertically down, which is mg, where m is the mass of the rod, and it is acting at half its height, L by 2. So, the torque about the finger, which I will call point O, so let me call it point O, is going to be mg times the distance shown here by blue, this distance which is nothing but L by 2 theta approximately, because theta is very small. So, it is mg L by 2 theta, and therefore, the equation of motion tells me that I theta double dot is going to be equal to mg L by 2 theta, where theta double dot is alpha is angular acceleration. Let us take this to be a uniform scale. So, let us take I to be, to understand the phenomena, ml square by 3. So, the equation becomes m L square by 3 theta double dot is equal to mg L by 2 theta. I am going to cut m from both sides, 1 L goes away, and I get theta double dot is equal to 3 g over 2 L times theta. That is the equation that describes the motion of this rod. So, the equation I have is theta double dot is equal to 3 g over 2 L theta, or theta double dot minus 3 g over 2 L theta is equal to 0. I just missed this 2 factor of 2 here. So, this should actually be 3 g over 4 L theta. So, the correct equation that I have is not this, but theta double dot minus 3 g over 4 L theta is equal to 0. The solution is very straightforward. If I take theta to be equal to e raised to lambda t, I get lambda square minus 3 g over 4 L is equal to 0, or lambda equals plus or minus square root of 3 g over 4 L, and therefore, general solution for theta as a function of time is going to be equal to some constant a depending on the initial conditions, e raised to square root of 3 g over 4 L times t plus b e raised to minus 3 g over 4 L times t. To understand what is happening and why this longer rod is easier to balance, this term is the second term, b e raised to minus 3 g by 4 L t is not important, because what makes theta grow with time is the first term. So, let us focus on that term. So, I can roughly write that theta as a function of time is equal to some constant a e raised to square root of 3g over 4L times t. So, let us see now what I am describing is this is a vertical rod. It initially got displaced by a slight theta and now it is moving with theta t equals a e raised to square root of 3g over 4L t. Let us say now if the center of mass, if Cm moves by distance x Cm, that means if the center of mass has moved by distance x Cm with respect to the finger, the rod falls. So, x is nothing but x Cm is going to be L by 2, which is the distance of, for small angles, L by 2, distance of the center of mass from the finger, times theta t, which is going to be a L by 2 e raised to square root of 3g over 4L t. So, time taken for this center of mass to move distance Cm is going to be equal to, let us take the log of both sides, log x Cm is equal to log of Al by 2 plus 3g over 4L square root of t. So, t is log of x Cm divided by Al by 2 divided by square root of 3g over 4L, and this gives me time is equal to some constant, which is this log x Cm by Al by 2 divided by square root of 3g over 4L, which is nothing but square root of 4L by 3g times a constant. What you notice that time required for Cm to move x Cm increases with length. So, longer the rod, more time it takes for it to cover a distance so that it starts falling, and if it gives you more time, then you have more time to adjust your finger so that you again bring the Cm back to exactly vertically above the finger so that the rod gets balanced. So, longer the rod, more time a person holding the rod gets to balance it, and therefore, you can balance it more than when the rod is shorter.